As I mentioned later on in this unit, we're going to be like doing actual chemical reactions. You're going to predict, like if I give you these two reactants, what products would you make out of this chemical reaction? To understand that, you really have to understand naming. So for the warm-up and the second part of the formative today, because the lab shouldn't take you too long to do, I gave you some more naming practice just to make this transition to like predicting products a little smoother. So the first question you have to ask yourself when you're naming is what? Yeah. Is it a metal or is it a non-metal? So arsenic, number one, is arsenic a metal or a non-metal? Well, arsenic's right there. It's actually kind of a trick question. Because arsenic's a metalloid, but if you're doing, it's covalent if it's non-metal plus non-metal, typically, or metalloid plus non-metal. So in other words, we have to use the prefixes here. So you see 4, what's the prefix for 4? It's tetra. AS, that's arsenic, so you'd say tetra, arsenic. And then 10, what's the prefix for 10? Deca. Now, when it's paired up with an oxygen, you typically drop that last letter, so you'd say dec oxide. If you say deca oxide, it isn't technically wrong, it's just not really like the most common way it's said. Yeah, go ahead. No space, yeah, no space between like the prefix and the element, but there is a space between like dec oxide and arsenic. Okay. All right. Then looking at number 2, so vanadium, V, is that a metal? Metal or non-metal? Or I guess metal, non-metal, metalloid. What would that be? V be a metal, yeah. All right. So then you got to ask yourself, if it's a metal, is it a transition metal? Do we know the charge that vanadium has? And you can just look at the periodic table, and you see V is in group 5. You know, the transition metals are 3 through 12. So that's a transition metal, meaning whenever you write out the full name, you're going to have to say vanadium, but then we're going to have to use parentheses to specify the charge that the vanadium has. And then it's paired up with O, so you could say that's oxygen, so you would say oxide. But now we got to figure out the charge. How you figure out the charge is you got to remember charges balance out to 0. You know that oxygen has a -2 charge, or it forms a -2 charge, right? And there are 3 oxygens, so there are 3 -2 charges, which is a -6. So we have to cancel out a -6, and you have 2 vanadium atoms to cancel out that -6. Bless you. So what does the charge need to be on each of those vanadium atoms? 3. Good. Plus 3. So you would say vanadium 3 oxide. So informative, type that all one word just to make the answer key easier. Vanadium, parentheses, 3 capital I's, close parentheses, oxide. All right, look at number 3, ammonium phosphate. This one's interesting because these are 2 polyatomic ions. So you know it's ionic naming, but you got to remember what ammonium is. Now I wrote your polyatomic ions on the board for you, but like on a test, I'm not going to have those up there for you. You know ammonium is NH4. Now phosphate is a PO4. Ammonium's got +1 charge. Phosphate's PO4 with a -3. Now our charges have to get to 0. So how would I get us to go to 0? What would I need to adjust? Kelly, good. Yeah. Good. You need 3 ammoniums. And remember, whenever it's a polyatomic ion, and you're going to have multiple of them, that's when you put parentheses around that polyatomic ion. Otherwise, you'd be saying NH43, and that is just ridiculous. When you're putting these in formative, or if you're just handwriting them, you don't actually include the charges. I'm just doing that to kind of show my work, so you kind of see what we're doing here. So parentheses, NH4, 3, and then PO4. And when you're typing them in formative, just keep it all one line. Like you don't need to worry about subscripts or anything like that. Yeah, Casey? This should be capitalized. Good question. Yeah, I know I kind of wrote it sort of like it's lowercase. Yeah. Anytime you're going to write O for like an element, like for oxygen, you would capitalize it. Unless it's cobalt CO, you would just use a lowercase o. All right, last one, sulfur trioxide. Now this one's kind of easier because you see the prefix tri, so that automatically tells you this is covalent naming, right? So you would just say sulfur. There's no prefix there, that means there's one. Remember, you don't say mono for the first element, so that's why you don't say monosulfur. Tri is 3, oxide is oxygen, so it's just SO3. Okay, I'm hoping that's a little bit easier for you at this point. All right, so getting into our notes. Get my cursor over here. That's what we did last time. So properties of matter. So broadly speaking, there are chemical and physical properties of matter. And I think the difference between them are decently obvious. I think sometimes differentiating them can be sometimes a little bit trickier. A physical property is something you can observe or measure, and here's the key. You can observe it and measure it without changing the chemical identity. Meaning, if you want to if I gave you water, H2O, the physical properties of water are things you can observe without having to literally change water into something else. So the color of water, or the lack thereof, you can observe. The length of water, which doesn't really apply, would apply more if it's a metal, but the volume of water, you can measure that without changing water from H2O. The opacity, how clear something is, you can measure that with water. You can measure, opacity is referring to how much light can get through. So opacity, light transmission, how much light gets through. But a chemical property is something that does change the chemical identity. Meaning, if I want to see how acidic something is, you actually have to change the chemical identity. You have to run a chemical test on it. You can't just observe it or measure it with some sort of device. Same with reactivity. If you want to see how reactive something is, you have to do a chemical reaction, right? By definition, you are changing the chemical identity. Okay? Flammability. If you want to see how flammable something is, you have to combine it with oxygen. All right? Combine with oxygen. You can't just look at something and be like, I'm thinking that's pretty flammable. It's well, somebody at some point had to actually try to ignite that with oxygen. And then toxicity, right? This is the wild thing about berries. You ever thought about the sad fact that how we know that berries are poisonous or unpoisonous? I guess somebody at some point had to ingest it, and their body did a chemical reaction to that berry, and they're that's a poison, and they probably died, or at least got very, very sick, which is really sad. But you don't know if something's toxic without running a chemical test. Okay. Any questions about those? All right. So this slide is kind of just in words describing some physical properties. So if you see something like temperature or pressure changing, those would be you observing a change in the physical properties of a substance. Meaning, if you see something going from ice to liquid to gas, you see a phase change, those are all changes in physical property. Because the actual, if you see water going from ice to liquid to gas, it is still H2O. You didn't change, water didn't cease to be H2O just because it's in the liquid form or the ice form or the gas form. It's still H2O. Okay? So changing temperature is just physical property. That would just be a physical change. All right. Now looking at chemical properties, anytime a chemical property or a chemical change has occurred, you're going to see a new product, right? So if you look at this chemical reaction here, let me put this down for you. You look at this chemical reaction here. You got methane. Methane is CH4. And if you react methane with oxygen, you will get the formation of new products. So a chemical change has occurred if you get new products forming. Another thing here is, methane is flammable because when you try to combine it with oxygen, you actually got a change. So again, if you see a change in the actual, like the reactants that you put in, you actually get new products. That's you observing a chemical property or something. You're seeing a chemical change. Okay. Iron rusting. What causes iron to rust or something? Like what causes rust in general? Right? But
Lemon juice can cause rust where it's like leftover time.
you said lemon juice can cause rust? That's true. But like if you just see something like just sitting outside, like what's making that thing rust? Mars, go ahead. Oxidation, yeah. This is caused by oxygen. Yeah. So a lot of times, like if it's really good quality metal, they'll put a coating around that metal to prevent it from like prevent the oxygen from causing the rust. But like especially if it's like maybe older cookware or something, you'll start seeing some rust forming. That's coming from the oxygen reacting with it. Or if it gets like a scratch on it and you remove some of that sealant, that coating. Like a car, like paint prevents the metal in the car from oxidizing, but if you like get a scratch in the paint or like a dent or something, like that scratch that paint, then you'll start seeing rust forming. Okay, cool. All right, so kind of a good slide summarizing a chemical change versus a physical change. And we really have, it's kind of the same thing we've been talking about. A chemical change has occurred when you actually get a chemical reaction happening and you get the formation of new products. So when you combust something, like what I showed you on that last slide, combustion will always produce, no matter the fuel source, you always get carbon dioxide plus water. Okay. Rotting. You see a fruit rotting. That's like there's an actual chemical reaction happening within that pear where like bacteria and stuff are like breaking down the sugars in that pear and making it get all gross and stuff. Okay. Rusting, what we talked about, right? The oxygen is reacting with that metal, causing that chemical change. Digestion. When you're doing digestion, you're taking like your food that's like in a bigger, I would call it a macromolecule, a bigger molecule, and then you have a bunch of enzymes and acid in your stomach that will break down the bigger food into smaller and smaller building blocks. Now, a physical change is something that does not change the chemical identity. Melting. If you melt a popsicle, the popsicle isn't like all of a sudden becoming this new, made of like new chemical things. It's just melted. It's just a different state of matter. So in other words, matter changing form, and by changing form, we're talking about like, again, solid to liquid to like gas, right? Like those are just physical changes. You shred something, you rip paper, that's just a physical change. You're not chemically changing anything. Same thing, boiling. That's taking liquid, making it a gas. That's not a chemical change. Chopping wood, right? You chop wood, you didn't just like chemically change the tree. It's just a smaller tree. Just a tree in smaller pieces. Okay? All right. Last slide, and this is kind of unrelated, but it is something like whenever you'll see this becoming more of a thing when we're going over reactions. Solute, solvent, solution. It's something you should have learned in 8th grade, but a solute is the thing that gets dissolved, and the solvent, so solute gets dissolved, and the solvent does the dissolving. And then a solution is going to be a mixture. So it's the solute plus the solvent. Okay. So water they call water the universal solvent. Why would they call water the universal solvent if you remember from like biology last year? Trevor? Yeah.
Because like almost everything dissolves in water.
Yeah, basically everything dissolves in water. You are like 70-something% water, right? All of your cells are primarily made of water. Your blood, that will, be flowing all throughout your body, is primarily made of water. And basically your cells are just dissolved in water, right? It's just a bunch of like components floating around in water. Solute would be like, here it's copper sulfate, so this would just be like a blue crystally thing. Those would dissolve. You combine, copper sulfate plus water, you would get copper sulfate solution, this blue looking solution. Okay. Any questions about that? Not a whole lot to elaborate on that. It's just kind of more of a technicality thing. All right, so let me stop the recording here.